If you're new to this channel, you may consider subscribing and hit the bell icon so that you continue to receive the updates. Also, after watching this video, you may want to refer to some of the playlists that we have created for people who are interested in in-depth knowledge. These are the videos in the right sequence, which will give you thorough knowledge of the subject. Please share it with all others who might benefit. Let's get started.
In this video, we're going to take up a new case study that's known as the Internet Firewall Dataset. We all know essentially a firewall is a piece of hardware or software that monitors the network traffic, and based on the traffic signals, it decides whether it wants to allow an activity, deny an activity, drop an activity, or it wants to perform a reset. This dataset has about 65,000 rows. It has been obtained from Kaggle, and we have 12 features in total. Let's get started. So we begin by pointing to the dataset. We've already loaded it. This is the name of the data file. And we import the basic libraries like pandas, numpy, matplotlib, and seaborn, and also the warning. Once done, we move to reading the data. Using pandas read CSV method, we are reading the specific file. And just to get an exact idea about the number of rows and columns, we are checking it using df.shape. So we have a total of 65,532 rows and 12 columns. To get an idea about how these features look like, let's just randomly sample some of the observations from the data. So we are sampling 5 observations from the data set randomly, and this is how the data looks like. So we have features like source port, destination port, NAT source port. NAT stands for Network Address Translation. And we have NAT destination port action, which is our target column. This has these 4 levels. And then we have bytes, byte sent, byte received, packets, elapsed time in seconds, packets sent, and packets received. The firewall would typically be monitoring the traffic and would raise a red flag or take an action depending on the patterns observed in the traffic. Let's check the data types. All of these features look like numerics except for the target column, but let's see if we have any garbage entry. It might change the data type. So we check the data types for all the features. So we were right in guessing. All the features are integers except the target column, which is an object. Let's check for the presence of missing values in our data. So we can do this by doing isNull.sum. And if we do another .sum, it will give the total missing values in the data frame. We don't seem to have any missing value in our data. Let's see the distribution of the target column, which is action. And we would want to see in what proportion all the categories are present. It is known that it has 4 levels, but we don't know the proportions. So we can check the proportions by doing normalize is equal to true inside value count. Now we can see that the first 3 categories add up to more than 99.9% in this case. Why? Because first category itself is 57.4, second category is approximately 23%, and third category is approximately 20%. So if we add all these, we'll be essentially crossing 99.9% or more. And the last category is hardly 0.08%, or you can say 0.1%. That's very limited. So we will be focusing on identifying the first 3 categories majorly, because the last category where we talk about a reset option, that's very minuscule in presence. Now, one important thing is that while we saw the features were all numerics except for the target column, there is a different consideration that needs to be given to these port-related columns. Why? Because these are just the identifiers. These are nominal variables. There is no point saying a port number 56 is better or greater compared to port number 20 or something like that, because there is no numerical order. That's just the location. So we want to work on these port-related features separately rather than treating them like pure numbers. We are creating a list of nominal categorical variables and we are iterating over it. What we are trying to check is the name of the feature in uppercase. That's just for printing purposes. But we are checking how many unique categories are present. Are there certain source and destination ports which are commonly repeated? Because when you talk about a firewall, it may have some distinction relative to whether it's an intranet request or an internet-based request. We may have a local arrangement where it's specific to an organization, or it is something that's connected to internet. It may give some considerations based on that. So we are checking how many unique categories are present and also the value counts of these categories. Let's just print this for all 4 features. So for example, source port has 22,724 unique entries. Our total data points are 65,000. And this means some of the ports have been repeated multiple times. You can see this port 58638 has been repeated 840 times. But there are certain other ports which seem to have some minuscule occurrences or unique occurrences. So that's the case with source port. Similar is the scenario with destination port. It has lesser levels, lesser unique entries. You can see there are ports like 53, which alone is present 15,414 times. Likewise, 445 is present 12,891 times. So a lot of repetitions seem to be there in this data set when specific ports are concerned. Similarly, the NAT source port has 29,152 unique entries. 0 alone is present 28,432 times. And so is the case with NAT destination port. Now, these are categories identified as numbers right now, but we'd want to treat them like categories. The challenge with categorical variables, however, is that we need to do an encoding for them. Are we going to do one-hot encoding? Let's take this variable, for example. This has 29,152 categories or unique labels. If we add or convert everything into a unique column, this will mean that we add 29,000 columns for this feature alone, 2,500 columns for this feature, and the earlier 3,000 columns as well as 22,000 columns. That's not a practical solution to do one-hot encoding straight away, nor we know any specific order right now. So let's first check, is there a possibility to simplify these columns? For example, let's say this variable called destination port has 3,273 categories or levels. Is it so that some categories add up to 80%? And those categories could be maybe 15, 16, 17 categories. If out of 3,273 categories, just about 15, 16 categories add up to 80%, then we can keep them as individual categories and club the remaining categories into a bigger bucket called others. So that would lead to a simplification of this column. Then we can use it for predictions even after doing one-hot encoding. But if that's not possible, then we'll see a different alternative. So let's first check, out of these 4 features, how many features are such where a few categories are the vital few categories and the remaining are the trivial many. That's what we are trying to do. So we are writing a simple function, which is find categories up to percentage, which takes the value counts of the categorical feature as the input and then calculates the cumulative proportion. So we are going to do a cumulative sum and divide it by the sum total. We'll get the cumulative proportion. Cumulatively, a certain number of categories add up to 80%. We'd want to consider those categories as pivotal. And the remaining categories will club into a category called others. So we are calculating the cumulative sum, returning the selected categories. Selected categories are the ones which add up to 80%. Let's run this. This is just a function. We'll have to apply this function to all the categorical features that we just listed above. So we are saying for each variable in the list of nominal categorical variables, so we are printing the name of the feature and writing has these many categories as significant unique levels. Let's just see. So if you see, source port has 11,619 levels that add up to approximately 80%. But destination port has just 17 levels that add up to 80%. Likewise, NAT source port has 16,000 categories that add up to a significant chunk. But NAT destination port only has 2 categories that alone add up to 80%. So these 2 categories that we have become super important for us, and they can be used for simplifying these features. Now what we're doing is that we are taking the same function we defined above and passing the destination port value counts to it. It would give us a list of those categories that are the significant categories in a descending order of frequency. So if we were to look at value counts, this would have appeared on top with maximum frequency, and this would have appeared at the bottom with least frequency. Least frequency, not at the feature level, but right now amongst the critical levels that add up to 80%. There would be a long list of other categories, which goes up to 22,000, but we found these 17 categories. Of those 17, 56205, this destination port has the lowest frequency. We are checking how many occurrences are there for this particular destination port. So we take the specific column, filter it for the specific destination port, and check the number of rows. This returns 288. So any category in this column which has occurrences less than 288 would be put into the category called others. And that's what we are doing here. We are saying, let's do the value counts on destination port, check the frequency. If it is less than the minimum threshold of 288, such labels should be converted into others, and in place is equal to true. Then we are checking how many unique labels are there and the value counts again. So this leads to 18 unique categories now. Why? Because originally 17 categories were significant, adding up to 80%. One more new category that's been introduced that's called other. And now you have 18 categories. So from 22,000 odd categories, we've reduced it to 18 categories. And now we can easily perform one-hot encoding. We can first visualize this also using a count plot, and then we can do a one-hot encoding. Sorting it in a descending order, this is how it looks like. And now we are simply applying get dummies from pandas to convert this into a one-hot encoding. 17, 18 columns when you have 65,000 rows would not be really a problem. But of course, 22,000 columns would have been a problem. So earlier we had 12 columns, now we have 28 columns. That's where we are. Now the same treatment we are checking for the NAT destination port because it only had 2 categories that were adding up to 80%. So we are applying the same function and checking what are those 2 categories, 0 and 53. 0 has the highest frequency, 53 is the second highest. And let's check how many occurrences of 53 exist. What's the frequency? So we're filtering the data for this particular destination port and checking the shape of the data. 15,094. Now we are taking this as the threshold and applying the same treatment. So we are saying if there is any other category within this column called NAT destination port, which means any other port ID which has occurrences less than 15,094, we want to convert it to other. So eventually we'll have just 3 categories here, 0, 53, and other. And we can simply create a count plot if we want to visualize it. Here's how the occurrences. Others, notice, has multiple categories, thousands of categories clubbed into one. But these 2, 0 and 53, were the significant ones. Once again, we can apply get dummies to this to convert this into a 0, 1 kind of a column. Now comes the tricky part. We still have features like source port and NAT source port, which may contain critical information, but we can't simplify them with the kind of encoding that we've just done for the other variables. Why? Because they had too many categories. About 15, 16,000 categories add up to 80% for these columns. So for this, we will do something that's known as the target encoding. As a preparatory work for target encoding, we need to convert our numerical column to a category or a string format. So that's what we are doing first. And then we are applying a label encoder for the target column. Target encoding is a supervised encoding. We've covered target encoding as a part of our feature encoding tutorial. You may refer to that tutorial to get further understanding of how target encoding works. And we've done a comparison between other types of encoding as well. Now, target encoding requires the target column to be encoded to begin with. And for target column, we already have a basic encoding that's known as the label encoder, which is nothing but an alphabetical encoding. So we are calling label encoder from sklearn preprocessing and doing a fit transform on the action column. This converts the action column, which was an object type variable, into an encoded column. Now, for this particular encoding that we are going to try, we may have to install the category encoders. So what we will have to do is we have to do a pip install category encoders. You may run this, it takes some time, and then it'll be installed. Now, once that is done, we can move to importing category encoders, and we can call it by an alias that's CE in short, category encoders. This category encoders provides us the target encoder. Please note, we also have a target encoder in scikit-learn, but at the time when I'm creating this video, it seems to have some functional issues, and that's why I'm not using it. I'm using category encoders. Category encoders would need the input on which column we want to apply this encoding. We are mentioning that input is the source port, and when we do a fit transform of this, it requires the data and the target column. This is a supervised encoding, like I said, so it looks at the target and then does the encoding, but it does not do the leakage. So you can see now source port has a very different representation. And we would like to do the same treatment for the NAT source port. So we're converting that again to the string, and we are just informing the category encoder that this is the column. We could have done it for multiple columns together, but we're doing it one at a time because this is new for you. So we are just doing it for NAT source port separately, as we could have passed the list also. And then we can mention the data frame and the target column, and let's just apply this now. So the NAT source port earlier, if you see at these numbers, now it has a different kind of an encoding. Next, we move on to fitting the model. But just one last step that we want to perform before we apply support vector machines, and that is scaling the data. So we know support vector machine also uses distance-based logic because it tries to maximize the margin. Now, we have so far not treated the outliers, nor it is recommended for this kind of data to treat the outliers. Please understand, a firewall would flag something as an unusual activity based on some abnormal numbers, and those would tend to be outliers naturally. So if we actually treat the outliers in this case, we'll probably be making our data weak, and our classifiers would not be able to do a good distinction in that case. So we don't want to modify the values that have been given to us. We would rather want to go ahead with the values as. Now, when you have outliers in the data, if you still want to have the data on a comparable scale, the option is robust scaler. Why? Because it does the scaling using the median and the IQR. So we will apply the robust scaling to the data after splitting the data into train and test set, and then we'll fit the model on the trained data. So we importing the robust scalar, we calling the support vector machines from scikit-learn, we calling the train test split, and the classification report finally to evaluate the model. Let's first segregate the data. So we are separating the X and Y variables. The Y variable is clearly defined. That's the action column with 4 levels. And X variables would be everything else. So from the overall data frame, we are dropping the action column and retaining it as the Y variable. And then we are calling the train test split, where we are giving the test size as 0.2. Now, the data was a little skewed with respect to a particular class, and that's why we are mentioning stratify is equal to Y. This ensures that whatever was the imbalanced class would be distributed in the same proportions in our training and test set. Once the split has been obtained, we are applying the robust scalar, fit transform on train, and just the transform on test. That's what we always do. And then we are instantiating the support vector machines model, support vector classifier to be precise, with a linear kernel to begin with. We know that we have multiple choices like RBF kernel, polynomial kernel, and we can try a couple of hyperparameter values like C and gamma, but we are not trying any of that to begin with. We are going with a simple linear kernel, and we'll see what the performance of a baseline model. We're doing a fit, and then of course, once the model is fit, we are doing a predict on train, generating a classification report, predict on test, and generating a classification report. So a lot of steps written together, but these are the standard steps that you must be very familiar with by now. Let's run this and see what's the kind of output we get. So we seem to have gotten output, and the output looks pretty good for at least 3 categories out of 4 categories in our target column. So you have a recall, which is 100%. Precision is almost to the tune of 100%, except for 0.99 here. And the overall accuracy is also great. Let's look at the test performance. Test performance is again very consistent. The recall is 100% for the first 3 classes, and precision is again very comparable with the trained data. So we don't have an overfitting issue as such. But we have a problem with the 4th class. I can imagine why this is a problem. Is there something wrong with the model to begin with? Probably not. The answer lies in the fact that this class has a very minimal occurrence. If you remember, compared to the overall data, this class was highly imbalanced. This was to the tune of 0.1%, which is very limited. So 99.9% of our data was the first 3 classes. This class was minuscule in occurrence, and that's why the model has not been able to identify it very well. We can, of course, try a class imbalance treatment, but if the primary motive was to identify the most common actions taken by the firewall, then we've been able to do pretty well at that, because the train and test performance gives us 100% recall and almost 100% precision. And this is without doing any tuning. In fact, tuning might not even be needed here, because the issue is not with the linear kernel. The issue lies with the imbalanced data. If we have more observations of this particular 4th class, which is labeled as class 3, we'd be able to do better in that case. This tutorial in particular emphasized on the data preparation, particularly from the encoding point of view. We talked about different kinds of encoding, simplifying a column, doing a one-hot encoding versus the target encoding, and that was a tricky part. And we also realized the importance of, at times, not treating the outliers, because it may otherwise affect the quality of the data. Hope you had some takeaways from this. Thank you.